A very good evening to Sir Azri and my teammates. My name is Michelle and we are from Group 10C. And our group is in charge of designing a nuclear power plant which need to produce total of 3,000 megawatt of power to serve the future needs for the major cities in Sarawak. This is the schematic diagram of our nuclear power plant. So as shown in this schematic diagram, we design our nuclear power plant into three circulations, which are the primary circuit, secondary circuit, and the tertiary circuit. In primary circuit, it consists of a reactor, a pressurizer, steam generator, and coolant pump. So the nuclear fuel uranium-235 is used in a pressurized water reactor (PWR) to undergo the nuclear fission chain reaction, which produce large amount of heat. So the heat is then transferred into the water inside the primary loop and flow into the heat exchanger, which is the steam generator. So the heat is being transferred through the walls of the tubes inside the steam generator to the lower pressure secondary loop of water. So in steam generator, the water of secondary loop will boil and turn into steam. The pressurized steam is then fed into the turbine with the high speed which drive an electrical generator connected to the electricity grid network to produce electricity for transmission. So after the steam enter the turbine and hits the turbine plate with high speed, the steam lost energy and start to condense and flows out the turbine in saturated liquid vapor state with high quality X. So the mixture is then cooled down and condensed in a condenser to become liquid and pumped back to the steam generator. The tertiary loop here consists of condenser and also the reservoir.
For the assumption part, the overall assumption is we assume the ideal Rankine cycle for the whole process. The process will consist of steady flow devices, and change in kinetic energy and potential energy are negligible, and there is no work interaction. The assumptions for the secondary loop is we assume the turbine inlet pressure P3 equals to 6.5 megapascal, while turbine inlet temperature will be T3 equals to 300 degrees Celsius. The turbine outlet pressure P4 will be equals to 5 kilopascal. The boiler and condenser will not have any work, while pump and turbine assumed to be isentropic. The thermal efficiency of Rankine cycle will equals to 1 minus Q out over Q in. The process is assumed to be Rankine cycle. In our design of secondary loop, we assume the value of inlet pressure of turbine P3 to be 6.5 megapascal. While for the outlet pressure of turbine P4 is assumed to be 5 kilopascal, as the turbine will give higher efficiency between the outlet pressure range of 2.5 to 7.5 kilopascal. For the inlet temperature of turbine T3, we assume the value to be 300 degrees Celsius. By performing all the calculation using the Rankine cycle concept, the efficiency we got is 0.38. To find the mass flow rate of the secondary circuit and the ideal work turbine output, which is 3000 megawatt, we use this formula to get the mass flow rate of the secondary circuit. In order to find Q in for the secondary circuit, we use another formula, Q in equals to mass flow rate times Q in. To find the heat generated for power in megajoule, we use this formula and we will get 7900.72 megajoule. And finally, to find the actual power produced from calculation in megawatt, we assume that turbine has isentropic efficiency of 18% and isentropic turbine work equals 3000 megawatt, and we will get 2400 megawatt, the actual work.
Why Rankine cycle? There are a few reasons we choose to use Rankine cycle instead of Carnot cycle. Firstly, at state 1, the water is saturated liquid state, and state 2 will be delivered as compressed liquid. The isentropic compression, which is process 1 and 2, involves the compression of a liquid-vapor mixture to saturated liquid. It is not practical to control condensation process precisely with desired quality at state 1. When the quality is greater than zero, it can result in damage to the pump. Secondly, current cycle requires the boiler to operate isothermally. The isothermal heat transfer eliminates the possibility of using compressed liquid boiler feed or producing superheated vapor at boiler effluent. Thirdly, in turbine, the adiabatic expansion yields low steam quality in turbine feed. The presence of liquid droplets will cause erosion to the turbine blade. Moreover, current cycles require the condenser to operate isothermally. This means that we cannot allow the turbine output to be a superheated vapor, or this will cause damage to the turbine. Therefore, Rankine cycle is used to avoid all of these problems.
For the conclusion and recommendation, we can divide the secondary loop into three. This means that each loop of turbine will produce 1000 megawatt instead of 3000 megawatt. The mass flow rate of coolant in secondary loop will decrease to half, and this will lessen the burden of the turbine and it will not break easily. The thermal efficiency of our plant is 38%. To increase the efficiency of Rankine cycle is by superheating the steam to a higher temperature. By doing so, the average temperature will increase during heat addition. As a result, both network output and heat input will increase, which can lead to the increase in thermal efficiency. Besides, this method can also decrease the moisture content of the steam at turbine outlet, which can preserve the turbine and reduce the aeration to the turbine. Secondly, we can increase the boiler pressure at which the boiling temperature of the steam will increase. When the plants operate at pressure greater than 2.20 megapascal, the thermal efficiency will be higher. However, this method will increase the moisture content in turbine outlet. To correct this, we can reheat the steam at secondary circuit. Last but not least, the conclusion is that although the calculation for chemical engineering thermodynamic 1 has been utilized in the concept of Rankine cycle, by assuming the isentropic and the steady flow device, we are able to get desired output of 3000 megawatt to serve for the future needs for major cities in Sarawak. The thermal efficiency is 38.38%, and the heat generated by reactor is 7900.72 megajoule, and the actual power produced is 2400 megawatt. Thank you.